From Zoom? Yeah. Perfect. Okay, so we will start, okay? So hello, everyone. My name is Bruno Famola. I'm going to be the chair on this session on fluid structure interaction and solid mechanics. We have 3 presentations today. Our first presenter is Eduard Montellà, a postdoc from the University of Genoa, Alpes, and he's going to show his work on moving objects on sediment transport processes. Please.
Thank you, Bruno. So yeah, as he was saying, I'm a postdoc. I'm Eduard Montellà, and I work at l'EGI. It's an institute in the University of Grenoble, and today I'll talk about the role of moving objects on sediment transfer processes. A work I did in collaboration with Julien Chauchat and Cyril Bonamy, also from University of Grenoble Alpes, and Tom Su, who comes from the University of Delaware. And this work has been funded by SCRDP, which stands for the Strategic Environmental Research and Development Program from the US. And that's because in the US, there's a major concern for unexploded objects. Wait, I moved this. In the US, there's a major concern for unexploded objects, munitions or mines that are found on the seabed near the coast of the state. And these objects can be abducted and transported towards the beach, posing an important threat to the people that are taking a bath, that are enjoying the beach, etc. These objects may come from previous wars, military action, but also from current military training. And under certain conditions like storm waves or currents, they are found on the sea or on the seafloor nearby. So scientists came up with these different diagrams, as you can see in this slide at the bottom, where you can actually predict more or less the mobility conditions or the boreal depth under certain hydrodynamic conditions. But as you can see, they are a bit messy. It's quite confusing. So they don't follow a clear trend because the mobility and the boreal of these objects depends on many factors like the density and the shape of the object, the properties of the soil, the kinetics of the main flow. And a possible alternative is to rely on numerical methods. So this is where we are coming in. We're going to use SedFOAM as a starting point, which is a 2-phase solver for sediment transport applications, which originally stemmed from 2-phase Euler foam. In this slide, I'm basically showing a wide range of applications in which SedFOAM has been used. The first panel, the one on the left, corresponds to the granular collapse. I studied granular material that was put in a tank, in a reservoir. Then you open up the gate and let the granular material flow out and study this dense granular flow. In the middle panel, there's a case of ripple migration under wave conditions, and on the right, there's a case where unsteady effects on a oscillatory sheet flow was studied using LES. But as I was saying at the beginning, we are especially interested in the interaction between solid objects and sediments and fluids. So now let's consider the case that you can see on the top. So it's basically a cylinder or solid object that is placed above the sediment layer. And then we increase the fluid pressure on the left side. You can also see it as increasing the water level on the left side. And that induces an increment of the fluid pressure underneath the object. And there's a moment the pore pressure builds up and counterbalance the weight of the particles. At this moment, the material is fluidized, it starts behaving like a fluid, and it's carried away. The particles are carried away by the main flow. This phenomenon is called piping, and it's actually quite well reproduced with SedFOAM. But the thing is, like, when after piping, as you can see, the object doesn't move. It doesn't go down under the action of gravity, which is not very realistic. At the bottom, there's a similar case that was portrayed by Benjamin Tsai, who studied the scour erosion around a pipeline. So he was indeed able to capture the scour features, but at the same time, the object, again, it looks like it's floating, and we need to improve this feature. So in order to accommodate the movement of the objects, so we are going to adopt two different strategies. On one hand, we're going to use the overset mesh that I guess you are all familiar with. Basically consists of having two disconnected meshes, and then you get the final results interpolating the data from the two meshes. The other strategy is basically consists of deforming the mesh. So in this case, the topology of the mesh is modified, but the connectivity between the cells remains unchanged. And here at the bottom left, so I'm basically indicating what kind of mesh I'm using for each case I'm going to show you. But before I jump into the results, I'd like to say a few words on the mathematical formulation that we're using for SETFOAM. We are solving the mass and momentum equations for the solid and the fluid phase separately. Here we have the momentum equations for solid on the top and the fluid at the bottom. Here I'm not going to go through the details, but I guess I can mention the different contributions. Maybe I can do like this. So here's the contribution of gravity, buoyancy, the drag that allows the coupling between the fluid and the sediment phase. This is the solid pressure that comes from the particles, the contact particles between the particles itself, the frictional shear stress, and finally the excess of fluid pressure. But because we want to deal with dynamic meshes, we need to rewrite this expression in the integral form over an arbitrary moving volume. So basically, we need to introduce the velocity of the grid in the advection term. But apart from that, there's no major changes in the code. So our first validation case consists of a piston or a horizontal disc that moves downwards and stops right before touching the sediment bed. So when the disc is moving downwards, it distorts the fluid field. And in turn, that creates some turbulence or some vortices that generate the resuspension of the sediment. In SETFOAM, in order to reduce the computational cost, we're basically considering an axisymmetric domain like this one. So this wedge is where the numerical simulation is actually taking place. You also see the disk in orange here and the overset mesh that corresponds to this translucid box. So this is the animation that corresponds to the numerical simulation. You can see that after the impact, well, not the impact because it doesn't touch the sediment. So after the plate stops, so it modifies the form of the seabed. And what I found particularly remarkable is that the advancing front that we see here of resuspended materials looks very similar to the one that was observed in the experiments. So qualitatively, we are following more or less the same trend, but let's see what we have quantitatively. Here in this slide, there's a plot of the evolution of the resuspended material. What we see is that in our numerical simulations, the maximum of resuspended material, so the peak, is slightly shifted towards the right. And the rate of settling particles is a bit faster in our numerical simulation compared to the experiments. But overall, there's a good agreement. But up to this point, well, this case I was showing you, I was showing you a case of prescribed motion. So when an object moves from point A to point B, now but we are interested in the response of a solid object under the action of hydrodynamical and granular forces. So to do so, we need to implement the 6 degree of freedom library in SETFOAM. So here's the list of different forces that can actually act on our object. First, we have the contribution of fluid pressure, solid pressure, viscous forces, frictional forces, buoyancy, and gravity. So once we add up all these forces, you can retrieve the acceleration, you integrate over time to get the velocity, and you do it once more, you get the displacement. And a very similar reasoning can be applied if you are interested in the rotation, but then you need the angular acceleration. To validate the 6DOF, we'll start with a very simple case. It's a falling sphere in a viscous fluid, so no sediment here. As you can see, we're using the morphing mesh in this particular case, and the sphere is slightly denser than the surrounding fluid. We can track the evolution of the position of the sphere and the velocity. What you see is that the sphere starts accelerating, and there's a moment that we reach the terminal velocity, and it follows. Our numerical simulation follows the same curve as in the experiments here displayed with the dots. And in addition to that, we also add the pimple foam solution just to make sure that we did the proper implementation of the 6DOF. And you can see it follows exactly the same curve as set foam. So we made sure that the implementation was correctly done. So we spice it up the simulations, adding some sediments, but we add them in a dilute suspension of a concentration of 0.05. In this case, well, the particles we added are neutrally buoyant, so it's the same density as the surrounding fluid. And you can see that the presence of particles basically increase the effective viscosity of the mixture, and that slows down the sphere. Now let's go one step further and see what happens when we introduce a sediment bed, a dense sediment bed. I know this video doesn't look amazing, but luckily it's happening what it's supposed to happen. It's a sphere falling on a sediment bed and being stopped by the sediments that basically all the particles, all the sediments are supporting the weight of the sphere. So we can track the different forces acting on the sphere during this process. What we see is that, well, at the beginning it starts falling in a pure fluid, so it starts accelerating. Here it's not very clear, but you can see the fluid pressure contribution start developing. That means that the drag force is increasing, but we are far from reaching the terminal velocity. The object impacts the sediment bed at this point here. Then the contact pressure, so the pressure of the particles acting on the sediment start developing, and also the frictional forces. So here, for instance, we have a map field of the particle pressure. And if you are familiar with DM simulations or experiments, if you track the contact network, they look very similar to this particle pressure field. And so basically this force is the one that contributes to slow down the particle. It goes back to zero, the particle, the sphere, sorry. It goes back to zero. And by the end of the simulation, the only force acting, the only surface force acting on the sphere is the contact pressure that balances the apparent weight of the sphere. Sorry. Now let's go back to the beginning, where I was showing you the case of scour erosion. So we can reproduce exactly the same numerical simulation, but adding the new feature of 6DOF in set form. So now we can see that in this animation that we are not only able to capture the scour, but also the self-burial process of the cylinder or the pipeline. And with that brings me to the conclusions. So I would say there's one main take-home message, which is that we have successfully implemented the 6DOF in set form to incorporate the hydrodynamical and granular forces acting on solid objects. And we test that with several benchmarks, I would say successfully, but it's true that these cases are pretty controlled, are easy to configure, but now we need to test them in more extreme conditions where hydrodynamical or frictional forces get very significant, and maybe we'll have numerical instabilities. So we need to test them in more extreme conditions. And also, I was showing you that most of the cases in 6DOF, I use morphing mesh, but because it was giving me less numerical instabilities. And the idea is to have overset mesh working as well with using set form and 6DOF. With that, Thank you for everything.
Last presentation. We'll have a couple of minutes for some questions from the audience and also from online. Anyone have a question for the presenter? I see that you have a comment online. I don't know if this is a question or
yeah, I can read it. Well, no, I don't need to read it. But... What? Ah, wait.
Yeah.
Okay, sorry. So the question is, how long does it take to run the piping case? What is the piping case? And the moving these, well,
I think the question is related to the computational time that considerations are taking.
Yeah, so overall, it's like 1 day. Most of the time it's 1 day, and using like, it depends on the case, but they range from 4 to 12 cores. But most of them it's just 1 day. But it's true. It's the fact that we are solving 2 phases that really builds up the computational time.
So we'll move on to the next presentation. Our next presenter is a PhD student from the University of Minho, and he's here to show his work on different membrane formulation to simulate the inflation process.
Thank you for the introduction. Good morning. My name is Wagner Galuppo. I'm a PhD student at University of Minho with the supervision of Professor João Miguel Nóbrega. I'm going to present the latest development that has been carried in the context of my PhD. We have entitled as Assessing Different Formulations to Simulate Membrane Inflation Process. And we have the industrial partner, Logoplast, with the contribution from Francisco Alves and Pedro Santana. Okay. So I divide my presentation in motivation, background, methodology, results and discussions, conclusion, and future work. Well, the main motivation is the vast applications where the membrane formulations can be used. Here you can see the airbags is a safety system for cars, mandatory nowadays. You have some non-permanent structures this is mainly applicable to stadiums where the players pass through. You have the roof and always the sides of the stadiums made from membranes. They stretch the membrane to cover. You have solar sailing, which is a tendency to the space exploration. So how to move very fast the spacecrafts. Here you have the morphing wing, which adapts with this inside the system, moving upwards and downwards to modify the shape of the wings, and pressure vessels. Well, the other motivation is harnessing computational modeling as a valuable tool to predict failures, optimize process, and enhance design across multiple domains. Here you can see another applications like the cover of a construction site. And here's some non-permeating buildings also. We saw several applications with a fast build-ups time, mainly during the COVID pandemic. Here's a spacecraft braking system where you have inflatable membranes to enhance the drag for braking the spacecraft. The formulation is simpler than the 3D, so the computational cost is lower. The availability of code in the finite area method ready to be used in the OpenFOAM, and OpenFOAM is open source computational library where you can use the classes and modify as you wish. Well, the background, the mathematical model, we have the mass times acceleration is the sum of the force. Then we have the body forces, surface force, and internal forces. For the body force, we consider the force due to the gravitational acceleration. Pressure forces is the pressure difference between the inner part and the outer part from the membrane. And internal forces is the response for the material for the deformations. So constitutive models, is responsible to relate stress to strain and then give us this measurement properly. Here you have the fourth order stiffness tensor, which is double contract to the deformation tensor. I will not go into the detail, but it ends up having to determine only these 5 terms due to the planar stress, which is a condition for the membrane formulation. But linear elastic deals only with the very small strains and deformations. And we are looking for hyperelastic, which deals with large strains, rotations, and so on. So hyperelastic, usually we use this in the total Lagrange formulation, the second Piola-Kirchhoff stress tensor. And we have this mathematical identity to transform to the Cauchy stress, with the true stress, which has the physical meaning for to measure. So the true stress, then we dot with the area normal vector, and then we obtain the internal forces. We can use implicit or explicit. Basically, implicit, the time depends, it neglected the inertia. The explicit, it considers the inertia. The increments in the implicit are loads, while for the explicit are time steps. And the solution system for the implicit, we have a function that relates a property at time t and the same property at time t plus delta t. And then we minimize to find the solution. While the explicit, we have the property at t plus delta t as a function from the same property at time t. Well, the first developments were considered the cell-centered, where we use the finite area cell-centroid. And then after the previous workshop, OpenFOAM, it was an insight to start the developments in the vertex-centered formulation. And the main difference is where the properties are discretized. So this is in the finite area cell-centroid, while this is in the finite area vertex. Well, and then the internal force modifies a little bit. It comes from the face edge to the internal face edge. Well, and the modeling approach, we can simulate a static problem where the sum of the forces are equal to 0, a quasi-static problem where the sum of the forces is approximately to 0, and a dynamic problem where the sum of the forces mass times acceleration. So it captures different behaviors and types of phenomena. So the implicit is recommended to be used in the static and quasi-static, while the explicit is recommended to be used in quasi-static and dynamics. So quasi-static reach the both worlds. Well, the first developments in this vertex-centered, we were facing a unstable behavior in the dynamic formulation, where we start to pull a sheet to the up. And then when we start to see the quasi-static approach, we notice that it passes right in the middle of the dynamic profile. So just to see how are the different phenomena that they captures, okay? So the modeling approach, we use the leapfrog method for the integrated Newton's second law of motion, which are calculated by these equations. And we have like the displacement positions lagged of delta t over 2 of the velocities, okay? So the leapfrog is because the way that it marks. And then if you notice here, you cannot self-start the leapfrog. So they have a method called a kick drift to self-start, or you use another method to start the algorithm. And what we did, so if you follow this, is an explicit approach to calculate. So we want then to calculate a quasi-static. So we artificially dampened this term here with this equation. Okay. And then we use as a first case to test a simple case where we can reach an analytical solution. So is the free inflation of a cylinder. We use the quarter of the cylinder with these material properties, okay? And with all the boundary conditions are symmetry plane. So the edges cannot move outwards from the plane that they are rest. See, here you can see how, sorry, it's not moving. Is it moving? No. Yeah, sorry, but at least you can see the gray profile, which is these gray dots here. They fit very well with the analytical solution, okay? So they are undamped. We didn't use the artificial damping. And the red, green, and blue, they use different values for the damping. And we see as the value increase, we saw over the increment of the damping effect as well. So the second case is the free inflation of a plate with these dimensions and these material properties. And we have this green edge with a symmetric boundary condition, so it cannot move outwards from the plane that they belongs. And the purple line are fixed displays, so they remain unchanged. They cannot move. For the pressure, we use this function here. So it's a ramp function until 3 seconds, and then it starts to move with a sinusoidal behavior. And here we study several, these 3 mesh refinements. So yeah, I needed this to play. Okay. But it's not. I don't know why it's not playing, so. Turn out to play. Anyway, I will play from here because. Yeah. This is the time refinement. Sorry, I will go back to the mesh. But as the time we study then the time refinement. As the time refine, we notice overdamped in the system, which since it's an artificial damping, is not physically, is just numerical. Okay. Then this is the mesh refinement study. As we refined the mesh using this delta T, we didn't notice a big difference between the mesh refinement. So that's why we use the coarser mesh to simulate. Okay. And so here is the time refinement that I was talking about. And to overcome and to let the problem to not be dependent on the time refinement. So as we refine the time, give us a proper physical behavior for the problem. We use the quasi-static. So the difference between this and the one before is that the one before, we save the time every time step increment. In this one, we do inner loops internally with the pressure development. So the pressure in here increased to this point. Then we keep moving, calculating the resultant force in a point, the maximum resulting force below at 0.1 Newton, for example, and then we move forward. Then we increment the pressure, calculate again, find the equilibrium. So increment pressure, find equilibrium, increment pressure. So in this way, even refining the time, we could have the same dynamic behavior for every case. Here is just to show the, sorry. How the same case with the quasi-static approach and explicitly. So you can see the red profile is always lag from the blue one, while the blue one is the quasi-static approach. And just to show the main application that I use, this is to simulate the plastic bottle producing process, which logoplasty uses. I will just play once. So you can see the modes clamp the perisome. The perisome is a membrane formulation, okay? And then pressure is blown from the inside, pushing it towards the mold walls. You see? So they want this as a tool to reduce the waste of plastic or reduce the amount of plastic in a bottle. Okay, to conclude, the computational framework is developed. Simulation of the membrane inflation process have proven to be a powerful tool to aid in the designing various practical applications. In the context of numerical simulation, a comparative study was conducted between two modeling approaches, so the dynamic modeling and quasi-static modeling. An artificially damped calculation successfully achieved the desired dynamic response of the system, reduce the time step required to reach the force equilibrium, and improve overall stability. And as suggested, future works are the implementation and verification of implicit method for the calculations, incorporation of self-contact boundary condition to enhance the capability of the membrane capture the wrinkling phenomena, expansion of membrane capabilities to include the bending stiffness considerations like shells. We are thankful to the FCT for funding this project and Search and Mac for running our simulations. We would like to invite you to attend this OpenFOAM Iberia meeting, which will happen in November 2nd and 3rd. So thank you very much.
Thank you, Wagner, for the presentation. Any question from the room? Any question online? Then I will start. Currently the code apparently is not able to detect other membranes being touched against each other, right?
Yeah.
So you need self-contact way of implementing this strategy.
Yeah.
Do you have any known formulations in literature to account for this phenomenon, or do you have to develop it yourself?
Yeah, there are some formulations in the literature. Basically, it's tracking how the contact model with friction can heal or sleep or no sleep, partial sleep, you know. And but the main problem is because here I use the membrane, the points to track another object, you know, another numerical object. So, and here I have to self-track the membrane with itself, you know. This is a thing that I kind of trying to see how to do this.
Yeah. Any other question? Then let's take the speaker again.
Okay.
So our next presenter is Stefano Biondi. Sorry for the voice. And he's a researcher at the University of Florida, and today he's here to present his working on protection of marinas, quantifying wave dissipation by porous structure. Please.
Good morning, everyone. My name is Stefano Biondi, and I'm about to start a PhD at the University of Florida. I'm really happy to be here, since this is probably the room with the best air conditioning in the whole seminar, I think. And this is also the first time I'm speaking to a workshop, so I'm quite excited. But yeah, jokes aside, this is my master thesis work, which I've been carrying on in the last year on protection of marinas, which is aimed to quantify wave dissipation by porous structure with OpenFOAM-based numerical approach. So to give you a little background on why we're starting on this field, we have to talk about climate change and how the sea level rise and the frequency of extreme events is affecting coastal population and coastal community, which are by far a great fraction of the worldwide population. In Florida, especially, these communities have a real impact on the economy, and so studying a way to protect harbors and marina and having affordable and handful solution is gaining way more attention in the research. So to define what usually are the classical coastal protection, we can start talking about floating breakwaters, which usually show different problems in mooring on stability, and rubble mount breakwaters, which clearly they're not suitable for every environment and they're really expensive to build. So a possible solution we came out, and which is common in the literature and we want to develop as the bad weather as possible, are the slotted wave screens. These structures are easy to build, assemble and maintain, and require way less material than the previous two. We can play with porosity of the screen so that we can get lesser forces on the structure, and moreover they're environmental friendly because they allow flushing and so preserving wildlife and water quality behind them. So how are we gonna study this kind of devices? We have to choose a parameter to define their performance, and this parameter is we decided to be wave dissipation. And to do so, we need a numerical environment. We decided to use an OpenFOAM to compute the whole hydrodynamic field in the structural proximity. So the outline of this presentation is going to be by starting to define which are the slotted wave screen design criteria and their geometries, so that we can develop a suitable CFD numerical model in OpenFOAM, explain the method and validate the numerical model we developed, so that we can discuss the result and choose a proper wave screen design. But let's start with the design criteria. The parameter we decide to use are 5, particularly. The first two are the submergence and the porosity, which represent the first one, the distance between the mean water level and the bottom of the structure, and the second one, the gap width. Then we let the model have different combination of inclination of the gaps, we're going to call alpha, and 2 values for the thickness. And the last parameter we focused on is the number of the slits. This parameter especially answered the question, what does it change if I spread the porosity in 2 different ways, for example, using 6 gaps of 5 centimeters each or 3 gaps of 10 centimeters each. We decided to use 3 parameters for the three values for the first 3 parameters and 2 for the second, getting a total of 108 simulation required with the structure. Let's develop a numerical model. We use OpenFOAM and we need to generate a wave field. So we use the waves to foam tool in OpenFOAM. We use Python FreeCAD to parameterize the structure and get all the possible combination that we possibly need. And then Python scripts to parameterize the domain and adapt the domain every time we need it to different wave fields. So depending on wave height, wave period, and depth. Where we solved the turbulence with a K-omega SST model corrected with a buoyancy term in order to force the solution to a laminar one in the interface proximity and reduce the wave damping by considering the gradient of pressure of the interface. And then all the simulation were running parallel on Hypergator 3.0 by 16 core each. So this is how the mesh looks like. Is a 6 wavelength domain, which is more or less composed by 1 million hexahedral elements, million cells, and every simulation takes 20 hours to run. But these values may be varying by, of course, the parameter that we use as an input, of course, changing the period of the wave, we have a different length so that the mesh could be bigger or smaller. The model gets the information of the wave field by the wave steepness and the wave depth, and decides which Stokes theory approximates better the wave shape. And we kept the y plus in the log low region so that we solve the turbulence with wall function. As boundary condition, we use, of course, the way we solve at the inlet the wave that we want to solve, and this wave is developed with a relaxation scheme. This wave is then absorbed with another relaxation scheme at the outlet. The bottom is set to no-slip conditions so that we can simulate the interaction with the sea bottom, and the walls, the velocity on the walls is set to cyclic to somehow reproduce a repetition of a linear meter in the domain. The atmosphere is set to atmospheric pressure for the pressure. Let's discuss method and the validation of this model. The way we work on analyzing and calculating the wave energy start by calculating energy in one point in space and time by its contribution of potential and kinetic energy. By then integrating in space by a wavelength in a control volume along a wavelength, and then averaging in time these two contributions, and then summing them and knowing the energy in a wave period. We did it in 3 different scenarios. The first one is, of course, by using the model outputs, so knowing the values of velocity and surface elevation. In the second scenario, to compare it with analytic theory, so using Stokes or linear theory by the waves. And in the third scenario, by developing an experimental setup in order to compare with experimental features. So the first scenario, the numerical model, how does the model work? The first simulation that it runs is a free flow simulation, so with no structure, in order to understand which is the incident wave energy inshore and offshore with respect to the structure. By doing that, we know, first of all, the incident and wave energy, but also the contribution by bottom friction, which occurs on the inshore contour volume, and eventually every numerical dissipation that could happen. After that, we position the structure in the middle of the 2 contour volume, and we run again the simulation so that we can have an energy balance and understand which is the contribution of the structure in this energy balance by subtracting to the incident wave energy, the transmitted one, and the contribution by bottom friction. After that, we can define dissipation simply by the ratio of the contribution of the structure and the incident wave energy. By an analytical approach, we come up with the idea that the process that involving the wave dissipate, the energy dissipation is related to the Borda-Carnot equation. And as you can see in the right picture, the water comes into the gaps, accelerates, and then develops some vortexes where the dissipation is happening. But this was not enough. In fact, there's one other contribution on the dissipation, which is in the moment where the wave is encountering the structure, which is by the vena contracta, the vena contracta dissipation, which is calculated as the same way as the Borda-Carnot expression. To have a simple value of this dissipation, we had to integrate from the end of the submergence and the surface elevation. So on the wave height, the velocity profiles inside the gaps, so that we could understand how this dissipation works. Another way, the third scenario, so the experimental one. We run 42 different regular wave field with this parameter that are shown on the picture on a 20 meters wave tank at the ICEA wave department in Padova, where in this 20-meter wave tank we had 8 wave gauges positioned 4 before and 4 after the screen in the sense of the motion. And the generation were made by a piston wave maker and absorption by a sponge layer. And we built just one structure, a wooden one, which was a 90% porosity wooden 2 centimeter thickness with 8 slit wave screen, whole submerged. After we ran all the 42 simulation, we decided to check if if what we were talking about was kind of correct, and effectively the wave is accelerating inside the gaps and then is decelerating when it's time for the trough to go back, so that this dissipation happened twice. And we had to calibrate this contribution because effectively the wave's profile is, yes, the one that you use as an input on the left side, but on the right one you have a transmitted wave which is lower, so we had to calibrate that one. And after the calibration, we had an overall comparison between the physical experiment and the numerical results and the analytical theory, which in my opinion should show a good agreement in this plot, which is represented by, on the x-axis, by the wave stiffness, H over L, and on the y-axis is represented the wave dissipation. The red dots represent the physical experiment, the blank square, the numerical model outputs, and the blue cross, the Borda-Carnot theory, which still showed a little bit of overestimation of the value, because probably we still have to calibrate the parameter on the trough wave on coming back again. So then that the model show pretty decent work, we decided to run whole the simulation with just one wave field, so one wave height, one period, one depth, but all the different combination of geometries of the screen. The first two parameters that I want to show you are the thickness, which showed a little bit of increment in the two cases we analyzed. We decided to pick two values, 2.5 inches and 3.5 inches, which represent the standard aluminum panel sizes in American industry. And we decided to work with these two. We have a little bit of increase of dissipation with the second one, but about 5% more, but it requires 40% more material to be built. So we decided to stick with the thinner one and proceed with the other parameters. The second parameter is the number of slits. So the one that checks if there's a difference between 3 gaps and 6 gaps, for example, but with the same porosity. And as you can see for the second plot, there's almost no difference in the two ones. So we stick with the 3 slits because it's, of course, easier to build. The less you cut, the less you spend. With the last simulation results that we have, so the last 27, we decided to cut by 2 again, the 180, so we left with 27 one. In this plot, in this 3D plot, it's pretty easy to understand that the yellow line on the other side is what we're looking for. So bigger spheres, more yellow spheres is where the dissipation is bigger. But this on the left side looks better for one reason, because we check also how the forces are, how the pressure were distributed. And so by integrating the pressure, how the forces was by differencing the orientation. So you can see on this axis, we have the orientation degrees, where 0 means horizontal slits, 45 means inclined, and 90 means vertical ones. As you can see in this one, the forces are slightly less than the inclined and the horizontal, so we decided to use the vertical ones. This is just a video of the turbulence viscosity with the functional porosity. It just shows, it's just cool. I just wanted to show because it's cool, I think. And as you can see, with the more the porosity, the less the structure is porosity, the more the turbulent affects the dissipation. So as a conclusion, I would say that this model has been validated against physical experiment and analytical expression. The device that we will provide up to 68% energy dissipation. As geometry parameter, thickness and number of slits does not affect significantly dissipation. Vertical gaps, though, reduce forces and provide a little bit more dissipation. Whether submergence and porosity are the most effective parameters to consider. Therefore, we will conduct some analysis on which combination of these two will optimize the structure. For instance, analyzing if is it better to have a 20% porosity structure that goes up to the bottom, down to the bottom, or maybe a 10% that goes half to the whole depth of the field. By then, the preliminary design that we propose by starting the optimization of this device is 3 vertical slits with a 10% porosity and a submergence of 5 times the wave height. Thank you. If you have any suggestion, I would be happy to hear them.
Very much, Stefano. Any question from the audience, please?
Yes, I actually went in the opposite way. I tried to use more gaps, getting absolutely insane on computational cost, and it still didn't change. I should actually. I could go downward maybe to 2 or 1, maybe. You're talking about using less gaps, less slats? Oh, okay. Yes, no, thank you. That's, I appreciate that. Yes.
Any other question from the audience? So don't appear to have none from online. So let's take the speaker again. And with this, we will finish this session on fluid structure interaction in solid mechanics, and now go for the coffee break. So thank you all for attending.